Yeah, so we have to start with the discussion about angular harmonic motion today with all sorts of pendulums coming into that category: physical pendulum, simple pendulum, spring pendulums, etc. Last time we discussed about spring mass systems and their SHM. So let's continue from that point onwards. Just one more thing before we continue. So within that thing of simple harmonic motion of spring mass systems, we will also discuss about equation of SHM from the energy method. So the background concept behind this is that for any SHM, x equal to a sine omega t plus phi, if the body in concern, which is undergoing SHM, has a given mass this relation. Okay, so from this we can understand that if the mass of the oscillating body equal to m, then the kinetic energy can be expressed as this in terms of time, or it can also be expressed as, now in this expression, where if omega square is equal to k by m, or f is minus kx, this kind of relation, okay, then kinetic energy is half so m omega square can be expressed as k, okay? So it becomes half k a square cos square omega t plus 5. Kinetic energy is proportionate to cos square function of time. Okay. And potential energy can be expressed as half kx square. This is because f is equal to minus kx. Okay, so potential energy can be expressed as this kind of quantity. Okay, so This way we can express the potential energy as half kx square. So this, okay, because F is equal to minus kx. Substituting that. So potential energy, I mean, even if it is not, a regular spring mass system where K is the spring constant. So here we just understand that K is the force constant for the restorative force. So potential energy can be written like this, or in other words, potential energy is half K A square sine square omega t plus phi. Potential energy is proportional to sine square omega t plus phi. So the first important thing here is this thing, that the oscillation energy, in other words, the mechanical energy of oscillation, is the sum of kinetic energy plus potential energy. That becomes half K A square. So the energy of oscillation is proportional to A square. So this information that we have just seen above, I'll come back to it in a moment so you can note down, but this can also be understood on the basis of energy versus time relation. So if you look at the say the potential energy, let's say that's a sine square omega t plus phi term. So let's take the special case where phi is 0. Then correspondingly the kinetic energy will become this kind of a term. We have cos square omega t plus phi kind of term. And the total mechanical energy, which is the sum of these two, remains constant. So per cycle, there is a switch two times. So this is the relationship of energy with respect to time. So I'm just minimizing this for a moment, just go through this. We'll also see the relationship of energy with respect to position, and from that how to derive the equation of SHM from the work energy method. So we'll come to that also. But just go through this section once and let me know if there's any doubt, or take down the key points. Okay. So this derivation of potential energy that I've done below over here, I mean, it's obvious that if it's a spring mass system, then the potential energy is half kx square only. But even other than that, any SHM will result from a restorative force which is of the type minus kx, where k is a constant. So such a restorative force will have a potential energy associated with it according to that formula, that delta U is minus of work done by internal conservative force. So in this case, minus f dx integration. So that's how we will define the potential energy of an SHM as half kx square, where k is the force constant, or k is basically such that m omega square is equal to k, and d2x by dt square is minus omega square x. So finally, the important thing here is when we look at the relationship with respect to time, if the potential energy is proportional to the sine square function, because x is proportional to sine omega t plus phi, then kinetic energy will be proportional to the cos square function. Okay, and therefore total mechanical energy will become a constant proportional to a square. This is your kinetic energy function, this is your potential energy function, and therefore your total energy is a constant. It's a fixed amount of energy, constant or conserved quantity. Okay, now the other thing within this is that since we all just saw that potential energy is half kx square, this comes from the fact that F is equal to minus kx, and total mechanical energy was half ka square. So kinetic energy will become half k a square minus x. Another way to understand that is that kinetic energy was half k a square cos square omega t plus phi, which we can write as 1 minus sine square omega t plus phi. So whether we write it this way or that way, we can understand that. Yes. So now if you look at during the SHM, the relationship of mechanical energy with respect to position, the two types of mechanical energy with respect to position. So if this is the positive extreme and this is the negative extreme, you can see that always our kinetic energy will behave in this way, that it's maximum at the mean position and momentarily zero at the extreme position as it oscillates between these two. So kinetic energy is this type of relation, and potential energy is, let's say, like the inverse of this. It's minimum at the mean position and maximum at the extreme position. So naturally, your mean position is a stable equilibrium point, local minima of potential energy, and the sum of these two is constant, which is the total mechanical energy. Oops, okay. So this should be this one. This. This should be constant. Now, interestingly, the conservation of energy equation that is kinetic energy plus potential energy is a constant, where kinetic energy is half mv square, potential energy is half kx square. From this also the equation of SHM can be derived. So from here you can see that rate of change of half mv square plus half kx square should be rate of change of a constant on the other side. So differentiating this, half m into 2v dv by dt plus half k into 2x dx by dt should be equal to 0. Okay, now v is dx by dt and a is dv by dt, which is d2x by dt square. So from this we can write it like this, that mv into d2x by dt square plus kx into v is equal to 0, or the equation of SHM. So the derivation of this equation of SHM, so far we've always seen it dynamically, but now the derivation of equation of SHM for a given system can also be done from conservation of energy method. Okay. So this basically shows us that hence any system with constant such that potential energy is of the type half kx square is an SHM. This shows this, that any system which has the potential energy term half kx square, its dynamics will reduce to d2x by dt square is minus omega square x, and that means that it's an SHM. So this gives us an alternate way of solving those type of problems, those type of situations. Okay, so let's look at an example of the application of this kind of situation. So basically what I'm saying is there are many types of mechanics situations where application of work energy is much easier than application of dynamics. Okay. For example, anything which has rolling involved is a good case in point where something like that will happen. So just imagine we have this kind of a situation. Let's say this is a solid cylinder lying on a rough surface, and it's got two springs attached to its axle. So on the other side also, the axle, that spring is attached. This is some kind of a rough surface. The springs are attached to a wall. That kind of situation. Each spring is of constant K. So the side view diagram basically looks like this. You have the cylinder lying on a rough surface, and close to it there's a wall. And the cylinder is attached by these two springs on either side, attached to the wall via these two springs through its axle, and spring in the background also. This is a rough surface. This is a solid cylinder. Mass M, radius R. Okay. This length L. So the cylinder can roll without slipping on the surface. Yeah. So the cylinder can roll without slipping on the surface. So if we give it, and it's free to rotate about this axle at which the springs are attached. Find time period of its SHM. So I will show you the work energy method of doing this question first. Just get familiar with the question. I'll explain it in detail. So you'll see the dynamics method will be a little bit more lengthy. Okay, if we take it from equilibrium to a certain displacement x on either side and release it from there, there is restorative force applied by the springs, but there will also be friction which will prevent slipping at the point of contact. And ultimately, you'll have to apply the no slipping constraint that, the point of contact is at instantaneous rest and all that. And by that method, you'll be able to show that the acceleration is proportional to displacement but opposite in direction. That is d2x by dt square is minus omega square x. And ultimately from there, prove the SHM. But much more convenient will be to use the fact that rolling friction does not do work. So as long as this object is rolling on the ground, if you take the two springs plus the cylinder as a system, then its mechanical energy is conserved. So write the conservation of mechanical energy equation, and you'll see it's an SHM equation in energy terms, and differentiation of it will give you the SHM condition that d2x by dt square is minus omega square x. So that is going to be the preferred method in this type of a problem. Okay? Because we know beforehand that wherever there's rolling involved, if there's friction involved, then work energy relation will not involve friction because work done by rolling friction is zero. Okay, so hope this concept is clear to all of you, which I'm saying. Okay. That rolling friction does not do work, even though it provides force, but because it acts at a point which is at instantaneous rest. So the power delivered by rolling friction is zero, the work done by it is zero. So that kind of situation. So in this diagram, if the springs are in natural length, now and while it is rolling, so it might be going in either direction with maximum speed and rotating like this. Now after some time, if it's reached a situation where it's here, and by now the displacement is x. So the springs are also both of them stretched by x. But accordingly, the velocity of the center of mass and the angular velocity about the center of mass have reduced slightly in comparison because of the tension. Okay. So it's in this type of motion, it will be decelerating if it's going in this direction away from the center of mass. But anyway, so we will use the work energy relation, that the sum of kinetic energy of rolling plus potential energy of the springs is conserved. Because even though rolling friction acts, work done by rolling friction is zero. Okay, so this is for that system. So half mv square plus half I omega square plus 2 times half kx square, because there are two springs, is the conserved energy. Okay. Now here v is equal to r omega is equal to dx by dt, and I is equal to mr square by 2 for a solid cylinder. So putting those two into perspective here, this becomes rolling kinetic energy. You know that you can always write like this directly also. So here this will become write this like this. So this is 3 by 4 m into dx by dt whole square plus kx square is a conserved quantity or a constant quantity. So now just differentiate this. That should be 0, right? So 3 by 4 m into 2 times dx by dt into d2x by dt square plus k into 2x into dx by dt be 0. So you can take dx by dt common, actually 2 dx by dt, whatever. So we have 3 by 4 m d2x by dt square plus kx is 0. So this is giving you a value of omega square. So this is an SHM. First of all, it proves that, okay, with omega square's value is 4k by 3m. So the time period of the SHM will be 2 pi under root 3m by 4k in this case. Okay. So it's a spring mass system that is doing rolling while it's doing SHM, but because ultimately any SHM system will have a net potential energy is proportional to x square and kinetic energy proportional to dx by dt whole square. So we can take advantage of conservation of mechanical energy. So we can take advantage of that concept of conservation of mechanical energy equation, differentiate it and put it from that find out the equation of SHM for the time period. So that is this method of solving the equation of SHM using the work energy relation instead of using dynamics. Okay. I'll very quickly show you the dynamical method here also, and you'll see how much faster this is, especially if you're used to, directly writing kinetic energy for rolling object and all those kind of things. Okay, so I'm just taking you through the dynamics method of doing such a question.
So can
But
you stop for 2 minutes?
yeah, just a moment. Okay. So that same second diagram, when it was having a displacement of x from the mean position, at that if we look at the FBD, okay, and write the force and torque equation and all that, so you can see that the two spring forces are acting through the center of mass. It's 2 times kx, okay, and therefore there will be friction acting like this at the point of contact. Okay. There will be mg and normal reaction, and these forces together will contribute to a situation where the acceleration is like this and alpha is like this because the displacement was x in this direction. So if I go with the dynamical equations, I have 2kx minus friction is equal to ma. Okay. Then friction into r is equal to I alpha. Here I will be mr square by 2, and E is equal to R alpha. No slipping constraint relation. That velocity of the point of contact is 0. That means V minus R omega is 0. So that means E minus R alpha is 0. This condition. Now solving this, we will get the dynamics equation. And E is of course minus d2x by dt square. So what we'll do is in the second equation, take the second equation and divide it by R, okay, and substitute alpha as A by R from equation 3. So the second equation will become that F is equal to m by 2 A. And now substitute this in equation 1. So we have 2kx minus m by 2a is equal to ma. So 3 by 2 ma is equal to 2kx. So a, which is minus d2x by dt square, will become 4k by 3m times x, which is our equation of SHM. But you'll realize that it's faster than this to write the work energy relation, especially if you're very used to writing work energy relation in rolling type problems. Okay. You can see it's just a two-step process for this one. So this the fast method is kinetic energy of rolling plus potential energy of the springs is constant. So kinetic energy of rolling is always half m plus I by r square into v square from the constant and all that. And so we have, this will become 3 by 4 because this is half. Okay, mv square plus ax square is constant, and then differentiate this. So this will become 3 by 2 mv dv by dt plus 2kx dx by dt is 0. So you got this equation. So tell me when you finished with this part, then we move on to. Okay, so done now with this problem. Okay, let's look at another quick example where we have a spring mass system and it's in a vertical situation, and there is also sort of constraint relation coming into the picture. So there's an ideal spring like this, massless thread on both the sides. Thread is attached to fixed to the floor at one end, and it's fixed to a mass block at this end. So this is a massless smooth pulley. It's an ideal spring. This is massless thread. Now let's take numerical values also. Spring constant is suppose given to us as 80 newtons per centimeter, and the mass of the block is given to us as 2 kilograms. Okay. The block is initially being held at rest such that the spring is relaxed and the thread is taut. The thread is just about taut. Okay, it's not, neither it is loose but nor it is having tension. Now at t equal to 0, the block is released from rest. G is equal to 10 meters per second square. Find its time period of SHM, amplitude of SHM, the maximum extension of the spring, and X as a function of time, where X is the extension of the spring. So we have to do all these things. Okay. So this is not just about time period, it's a more complete problem. Okay. So let's try this question out. Okay, you can do this question by both dynamics method or by work energy method, as I've explained to you. But you will also have to take into consideration the constraint relation, whichever method you go by, whether it is dynamics or work energy, that when the spring extends by X, how much is the displacement of the block? It's not going to be X, okay, because the thread is going around the pulley like that. Okay, so I will draw three versions of this situation. The first is to illustrate the initial condition at t equal to 0. X of the spring is 0 and U of the block is 0. Now the other thing I'll establish here is the equilibrium condition first, because I'm doing it by dynamics first. So you'll realize doing it by dynamics is considerably more lengthy. But anyhow, if I'm solving this by dynamics, in the equilibrium state, the spring is also a little bit extended. The block is also below compared to that thing. Okay. So this is now suppose L plus X naught. And this is having zero acceleration. So it's the equilibrium state. So if it's at the equilibrium state, tension is balancing mg. Kx naught is 2 times T naught. So we have X naught is equal to 2 mg by K. Whatever that value is, we can check it out later. Now compared to this, if now we take a situation where the spring has got a further displacement of X or whatever. Now this has become L plus X, where X is basically equal to X naught plus some delta X. It's gone further down by X. So how much the block would have gone further down by? The displacement of the block, let's call that Y, would be equal to 2 times delta X. This is the constraint relation, first of all. So make sure all of you are clear with this. Okay. Comparing the equilibrium position with this, if the pulley has gone down by delta X, then the block has gone down by Y, which is equal to 2 times delta X. That's the thread constraint. So now the tension has changed because the tension in the spring has changed. So X is greater than X naught, so tension is greater than T naught. So this block now having a downward displacement of Y has an upward acceleration of T. So E is minus d2y by dt square, and we have T minus mg is equal to m. T is equal to 2kx. Oh, sorry. Kx is equal to 2t. And x minus x naught is equal to delta x, which is y by 2. So this equation is now telling me that kx by 2 minus mg is equal to ma, or k by 2 into x naught plus delta x. So this is my equation number 2, whereas this was equation 1. Equation 1 is basically telling you that so substitute that over here. See that So this term equals to this term. So we've got K by 2 delta X is equal to MA. And we had that delta X was equal to Y by 2. Okay. And A was equal to minus d2y by dt square. So you got the equation of SHM for the block. So y is equal to some amplitude into sine omega t plus some phase constant, where omega is equal to square root of k by 4. The time period is, so this is the proof of SHM and the time period part. Now we have to move on to the next thing, where equation of SHM and amplitude, and from that x as a function of time, where x is the extension and all that. We have to do those things also. So we'll come to that. Just note down up to this point on first. Sikita, we can't exactly use equivalent mass of 2m in that sense over here because there's a constraint relation involved now. Okay, now the thing is, see what is happening, the relation between x and y, what was that? If you see, y was equal to 2 times delta x, where delta x was basically x minus x naught. This was the relation between x and y. Okay, so x naught, remember, was, so what was the value of the spring constant? Let's pick up those things. 80 newtons per centimeter and m is 2 kg. Okay, so x naught is 2 mg by k. So this is 2 into 20 divided by 80. So 0.5 centimeters. And the time period before we do our things, let's calculate that. Was 50 newtons per centimeter. Okay. So the 8,000. So time period is 2 pi by 10 root 10 seconds, like this. Okay. Anyhow, so this is x naught. Okay. Now we can see that at t equal to 0, x was 0. The spring was relaxed. So therefore, from here, what is the value of y? So y at t equal to 0 would have been 2 into 0 minus x naught. So it's minus 2x naught, or the initial value of y is minus 1 centimeter. And the initial value of v at t equal to 0 was 0 because it started from rest. So if y is a sine omega t plus phi, so v is a omega cos omega t plus phi. So we can see that a sine phi is minus 1 centimeter and a omega cos phi is 0. So that means our phi should be minus pi by 2 and a should be equal to 1 centimeter. So y as a function of time is becoming a sine omega t minus pi by 2, where a is 1 centimeter and omega is square root of k by 4 and that value. Okay. Now if y is this, then we can also say that x, now if you invert this relation, this one here, you can see that x minus x naught is y by 2. So x is equal to x naught plus y by 2. So x is equal to x naught plus y by 2. So x as a function of time is, now you can see that x naught was 0.5 centimeters and amplitude divided by 2 is also 0.5 centimeters. So basically x as a function of time is, if you take 0.5 centimeters common, it is 1 minus cos omega t. You can see from here that x's maximum value is 1 centimeter. Okay, and that happens at t equal to t by 2, 3t by 2, so on and so forth. And x's minimum value is 0. So the spring ranges between natural length to a maximum extension of 1 centimeters. It never compresses. Whereas y as a function of time, The displacement of the block is according to that. Okay. So after deriving the condition for SHM, okay, that d2y by dt square is minus omega square y. Further, to get the amplitude and the phase constant and be able to write the equation of SHM, we need the initial conditions. So we made use of the initial conditions. It's in this. So from that we got the value of amplitude and the phase constant. So we got the SHM as a function of time, y as a function of time. Then using the original constraint relation, we can also go back and find x as a function of time, where x is the extension of the spring. So that is, for example, telling us what is the maximum extension of the spring. Like that, another question within this could have been that what is the maximum speed the block will achieve during the oscillation. So the answer to that is a omega. So we have already found out that the amplitude is half a centimeter. Sorry, the amplitude is 1 centimeter and omega's value we've got. So from that we can calculate the maximum speed. So these type of things which you might be used to doing using work energy earlier on, now we can do by the SHM method also. Okay, so Nikita, I hope you have understood the concept of the constraint relation here, and that we cannot use an equivalent mass concept directly over here, right?
Yes, sir.
Okay. Okay, so this is your y as a function of time. You can also alternately write this as minus a cos omega t, because sine of omega t minus pi by 2 is minus cos omega t. So now to understand the extension of the spring as a function of time, you go back to this, the relation between the position of the spring x and the displacement of the block from its mean position y. Okay. To understand y here, it is the SHM parameter. Okay. And the sign convention also we've taken is such that it is the downward displacement of the block from its mean position. So at the mean position, y's value is 0 and x's value therefore becomes x naught, which you can see from here. Okay. Also, you'll realize here that when x is equal to 0, x minimum, at that point of time, the block is at its y equal to minus a, that is the topmost position. And whenever x becomes its maximum value of 1 centimeter, y is it plus c, that is at the lower extreme, at the lowest position. Okay. So the block oscillates between minus 0.5 centimeters and 0.5 centimeters. So between minus 1 and plus 1 centimeter. A is 1 centimeter. So the range of the motion of the block is over 2 centimeter from its lowest to highest position. And the range of the spring is 1 centimeters from its lowest to highest. So there's that 1:2 relation between the two. Okay, so these are some examples of SHM of spring mass systems and the application of work energy. So later you try the above problem by work energy method also. By work energy relation method also. You see, it gives you more or less equally efficient method of solving the problem. Okay. Now let's move on to the next part of this chapter. Okay. Though the chapter is simple harmonic motion, but actually now we are moving on from simple harmonic motion to what we call angular harmonic motion. So it is an angular oscillation. So an angular harmonic motion is basically an angular oscillation such that the angular displacement is a harmonic function of time. So have some relation like this. This kind of a relation where theta is the angular displacement from a mean position, which is theta equal to 0. Then this becomes the angular amplitude, because the angular displacement varies between minus to plus of this amplitude, and rest of the things are the same. Omega is angular frequency, phi is the phase constant. Initial phase. The mean position is once again a stable equilibrium position, but this time it's an angular system. So the stable equilibrium implies that the net torque is 0. Net torque is 0, and there is restorative torque when displaced from equilibrium. So now from this, you can also see that the angular velocity at any instant, d theta by dt, is also a harmonic function of time. And therefore the angular acceleration is also a harmonic function, such that it is proportional to displacement, that is angular displacement, of course, from the mean position. So from this, we'll understand that the dynamical condition for angular harmonic motion is that d2 theta by dt square is minus omega square theta. That is, the angular acceleration is proportionate to the angular displacement from mean position and opposite in sense. So it is just a sort of rotational version of what is happening in simple harmonic motion as a oscillation along a straight line. In angular harmonic motion, it is happening as an angular oscillation about a fixed axis. Of course, when we say fixed axis, it's about what reference frame we are looking at. The axis should be fixed in the reference frame in which the motion looks like an angular harmonic motion. So even an axis which is fixed to the surface of the earth in another reference frame, which is, let's say, the reference frame of another planet or the reference frame of outer space, that is not a fixed axis because the earth's surface itself is in motion. So the whole notion of absolute reference frame and reference frame at rest and all that is actually relative in that sense. All reference frames are relative to each other. Okay, so the most natural example of an angular harmonic motion is something called a torsional pendulum, which is any rigid body suspended by something called a torsional wire. Typically, a torsional wire is made by twisting very fine fibers of metal into a sort of a rope, like phosphor bronze kind of. So that torsional wire has a property that if you twist it through an angle theta, then it applies a restorative torque. If you twist the wire itself, like a vertically suspended wire, if you twist it through an angle theta, then it applies a restorative torque of tau, which becomes minus k theta. So that is the property of a torsional wire. It applies a restorative torque tau when twisted by an angle theta, such that this is the relation. Just like a spring applies a restorative force proportional to displacement, a torsional wire applies a restorative torque proportional to angular displacement. So now a torsional pendulum is constructed using a torsional wire and any rigid body. So you just take this torsional wire, suspend it from some point, and take a rigid body of any shape. Of moment of inertia I. So when you twist it through an angle theta, it experiences a torque is equal to minus k theta. Now the quantity k over here is called the torsional constant. It is a physical property of the torsional wire. Notice that that torsional constant is different from spring constant because it has the dimension of force into displacement or force into length. It's expressed in Newton meter, whereas spring constant is expressed in newtons per meter in SI unit. Anyhow, so coming back to this, so this will experience an angular acceleration now, which is like this. So torque is equal to I alpha. So alpha, which is d2 theta by dt square, will become minus k by I times theta. So this is an angular harmonic motion with omega square equal to k by I, time period equal to 2 pi under root I by k. Okay, so just make a note of this, then we'll discuss some more aspects of angular harmonic motion. Okay, so for example, if we have a situation like this,
So can you scroll up for a minute?
yeah. So we have a rigid body which is in the shape of a dumbbell kind of thing. Two particles of equal mass, okay, attached by a massless rigid rod. And then this is attached to a torsional pendulum or a torsional wire of a given torsional constant K. So first of all, we have to find the time period for angular harmonic motion. So for that, it is given to us that the torsional constant is 20 Newton meters for the wire. The mass of each of those particles is 1 kilogram, and the length of that rod is, that massless rod is 20 centimeters. Okay. Now, if given an angular amplitude of 4 degrees, then find the maximum speed, okay, and the maximum angular acceleration for each of the particles M during their oscillation. And oscillation is angular, of course. Okay, so just take down the data of the question, then I'll take you back to the above portion once more. We try to work out this question, we'll discuss. The torsional wire is attached to the midpoint of the rod. You can assume that. That's how it will be in a horizontal equilibrium. Okay, so let's finish off this question fast. So first of all, you can see the moment of inertia of this will become how much? 2 times a particle of mass m lying at the radius of gyration of L by 2 from the axis. This is the axis of rotation. Okay. So this is L by 2 for each side. That's ml square by 2. So the omega square is, so we have the equation d2 theta by dt square is equal to k by I, the minus sine theta. So omega square is k upon, right? So time period is 2 pi. So here it will become like this. So when time period is coming like this in seconds. Now this tells me that the angular displacement will be like this. Okay, where omega is square root of 2k by ml square. That is the value of omega. So the angular velocity is omega into theta max cos omega t plus 5. So now these two particles, they are going to be in circular motion. So if you take the top view, when this is rotating at d theta by dt like this, these two particles will have the maximum speed when it's at the mean position. So that maximum speed will be L by 2 into that angular speed maximum. So it will be L by 2 into omega theta max. From here you can see. Okay. So it is 20 into 10 raised to minus 2 by 2 into omega, which is 10 root 10 into now this theta max was 4 degrees. So we convert it to radians. Okay. So into pi by 45. So this answer that we get will be in meters per second. So this will be the maximum angular maximum speed of the particles, and the maximum angular acceleration will be, of course, d2 theta by dt squares maximum. So that will be omega square into theta maximum. 1000 into pi by 45 in radians per second square. Okay, so these type of concepts come in for torsional pendulum based question. Okay, now we'll just take another 5 minutes to finish the last part of angular harmonic motion, which is physical pendulum. Simple pendulum will be a special case of physical pendulum. So what we'll see is that small oscillations are the angular harmonic motion situation. So by small oscillations, we'll see that it means oscillation of small angular amplitude. So physical pendulum is like this: a rigid body of any shape suspended through a axis about which it can rotate freely. So there is a fixed horizontal axis at the point P, okay, about which the body can rotate freely in a vertical plane. And if this is the center of gravity or center of mass, then the distance of the center of mass point is d, and ip is the moment of inertia about the axis at p. So these two things become important. So when it is at this kind of vertical position, this is the stable equilibrium position, because torque is zero. So that is the mean position of SHM, or angular harmonic motion. Now when we take the system from this initial mean position to a position like this, where now with respect to the original vertical line along which the center of mass was lying, now we brought the body to a position where the center of mass joined to that axle P, that is now at an angular displacement of theta. So you can see that at an angular displacement theta like this, mg will be creating a torque which will be like this. There's a restorative torque. Tau, which is like this. So just drawing this separately over here, this line PC is at an angle theta with the equilibrium position vertical situation, then the moment arm for the mg force becomes this, which becomes d sine theta. Okay. So the torque that this produces becomes mg d sine theta, and this torque is equal to I alpha, where alpha is minus d2 theta by dt square, and I is the moment of inertia about the point P. So we have the equation that mg d sine theta, that is the torque, is equal to ip alpha, where alpha is minus d2 theta by dt square. And it can be either side, clockwise or anti-clockwise. So now from this we can see that the relation that we get is not quite angular harmonic relation, because it is mgd divided by ip into sine theta. So this is not a harmonic, this is just an oscillation equation, angular oscillation equation. This is a restorative situation. But for small theta, sine theta can be approximated as theta. So that is where the concept comes in, that d2 theta by dt square is minus mgd divided by ip into theta for small angular amplitudes, for small angular displacements or amplitudes. So that means the maximum angular displacement should not be more than about 5 degrees. Then we can apply this approximation. So this is an angular harmonic motion with omega square equal to mgd divided by ip. So time period equal to 2 pi. So this is like a direct formula for a physical pendulum doing SHM with small angular displacement or doing small oscillations, what we call. Now the value of IP and D will depend on the geometry of the physical pendulum. Okay. So on the side we'll take an example also. So suppose our physical pendulum, just a thin uniform rod. Okay. And its point of suspension is the topmost point P. Then we can see in this case, the value of D will just be L by 2 if the mass of the rod is M and length L, and moment of inertia about P will be ml square by 3. So omega square, which is mgd divided by ip, becomes L by 2 divided by ml square by 3. So it becomes 3g by 2l. Time period becomes 2 pi. So if this is oscillating with a small angular amplitude back and forth like this, we'll have a time period. So like this. Okay, so people, with this we complete the theory part of simple harmonic motion. There is also a section called damped oscillation. Okay, we will discuss about that in the next week's lecture also. But keep in mind that that is not in your JEE advanced syllabus. That is only in JEE main syllabus, and again only the formula is there. The derivation is not there. So the main part of the questions from oscillations and SHMs are to do with simple harmonic motion of spring mass systems and various linear systems like we've discussed, and the two types of pendulums, torsional pendulum and physical pendulum. We'll see a couple of variations in problem solving also last time, but next time, but we'll basically theory wise, this is what it is, angular harmonic motion. Okay. So that's it for today's session, people. Make sure that you revise this section carefully, and now you can go ahead and complete the problems from HC Verma of simple harmonic motion. That will be quite sufficient for your JEE level practice actually. Various types of questions are there with all sorts of constraint relations, rotation involved and things like that. Okay, so that's it for today, people. Wish you all the best. Have a nice day. Thanks for attending.